part 2 of a two-part session. We began with the intro to radiology, so if you haven't watched part 1 first, start there. But this is part 2, and we're going to talk about the physical foundations. Some of these things will be things that you may have had when you were in physical science in middle school or high school, but we're going to cover them again kind of quickly. We won't necessarily need everything on all of these slides. Some of these are just kind of playing catch up. So some of our definitions we're going to start with. Matter is anything that occupies space or has mass, and energy is ability to do work or overcome resistance and kind of get things in motion. Typically is involved with that definition. Atoms we really aren't going to deal much with. Molecules are when you combine atoms. Again, I'm not going to ask you these definitions on the exams. I'm just kind of getting us all in the same place starting out. But the good stuff comes in the next slide when we talk about atoms just a little bit more. In atoms, you have negatively charged electrons that are in constant motion in an orbit around the outside of an atom. The inside of the atom, you have protons and neutrons. Protons are positively charged, neutrons are neutral, and they change the mass and the weight, but not the electrical charge. But protons and neutrons are in the nucleus. The electrons are circling around in an orbit outside, almost in shells. So mostly what we're going to talk about in radiology are going to be the electrons. We've already talked about how the filament heats up and boils off electrons. So we're going to kind of continue that and mostly talk about electrons. You can't take a radiology class without at some point getting the definition of radiation. Radiation is just energy, heat, light, or rays that are sent out as molecules and atoms undergo internal change. So in our case, we're pulling out these electrons, and then they go across the cathode stream and slam into that tungsten target, and that's where that internal change begins. When we talk about the internal change, that's where it starts, is we change those electrons into heat primarily and X-rays. The next time we talk about it again, the electrons that became X-rays get shot out of the machine, and as they're passing through the air or body tissues or even trying to pass through the walls, things like that, they're constantly trying to regain stability. And so the X-rays are trying to turn back into electrons. And we'll talk about that some more in just a second. Some different sources of radiation. You have cosmic radiation, which just filters to Earth from space. Our atmosphere protects us from a lot of that, but some radiation still gets through. Otherwise, we wouldn't be warmed by the sun. We wouldn't have the light from the sun. So those are two examples of radiation that we like, but there are other types that come through as well. Terrestrial radiation means the rocks and elements that are on Earth that naturally emit radiation. And I put in here that radionuclides deposit in our bodies. There are elements from the cosmic radiation, terrestrial radiation, or even medical purposes where we use radiation, like in the treatment of cancers and infections and things, where that radiation does come from our bodies out back into the air around us. Okay, isotopes. I'm just going to give you a quick definition here. It's not a chemistry class, but you remember the periodic table and the 150 basic elements that are present on the periodic table. Well, there are 1,500 identified isotopes of those 150 basic elements. And an isotope is just a specific atom that has the same chemical properties but a different weight or mass. And the best way I can explain this, again, I'm not a chemistry teacher, but you've got the 150 basic elements, And then you have their weird cousins. You're related, you're kind of the same, but not. So that's what an isotope is. It's very similar. It has the same chemical properties as the basic element, but it has a different weight or mass. So it's a little different. It interacts differently. Of those isotopes, half or more of them are unstable and radioactive. And that's the only reason it gets mentioned here, is because what's different is the number of protons, neutrons, or electrons. And X-rays, as they interact with different atoms, can bump electrons out. When they bump the electrons out, they create an isotope. Okay, that's where we get into the decay process. The decay process is really just talking about how the X-rays themselves are trying to become electrons again. They're trying to regain that stability. And in the process, they give off radiation. They're releasing that energy. And the decay process is really talking about how they either become stable electrons again and lose their energy as they do. So I'm not going to ask you a lot of questions about the electromagnetic radiation definition, but I've given you that there. Electromagnetic radiation is just electric and magnetic energy. It travels in waves, and you've got a diagram in your book that talks about the different types of electromagnetic radiation. It's everything from X-rays to cell phone signals to the microwave used to cook stuff in your microwave ovens, satellite signals. All of those things are electromagnetic radiation. Gamma radiation, I just gave you that definition, but I won't ask about it. It's similar to X-rays, but they occur naturally rather than being man-made. And I just mentioned it because if you talk to somebody that deals a lot in nuclear medicine or radiation, they may ask you or talk to you about gamma radiation. I just wanted you to hear it. Okay. Electromagnetic radiation, I've got kind of some characteristics listed here. They pass in a wave-like motion. They travel at the speed of light. They give off an electrical field. That's the electrical field that ghost hunters use to say that there's a ghost over here because there's an electromagnetic field. That just means there's some source of electromagnetic radiation. It could be a high power line that's got a short in it. It could be metal pipes. It could be a ghost. It could be a microwave oven on the other side of the wall. It could be a lot of things. But electromagnetic radiation is measurable and different. You can't, cook something by sitting on top of the radio, and you can't pick up a radio station with your microwave. They're different in the way that they function, even though they're all in the same family of radiation. Wavelengths and frequencies, we're going to talk about that for just a minute. With long wavelength X-rays, those are going to be low frequency, which means they're not going to occur very often. They're going to be low energy, soft X-rays. And with long wavelength, think about them being lazy. They're slow, they're not moving very much, they're low frequency. Well, as an X-ray, those are not going to penetrate the tissue very well. They're going to get absorbed instead. And when X-rays get absorbed, they cause damage, and we don't want that. So long wavelengths are not great, traditionally speaking. Short wavelength is going to be the type of X-rays that we prefer. They're high frequency, meaning that in a given space and time, you'll have more of them. They're high energy. They're hard X-rays. They penetrate more, and they aren't absorbed. So you get more useful diagnostic tool out of a short wavelength X-ray as opposed to a long wavelength X-ray. And quick quiz just to see if we were all paying attention earlier. Short wavelength is going to be a stronger X-ray. So was that created with a low kVp or a high kVp? And you may have to go back in your notes to figure out long wavelength and short wavelength and which type of kVp was involved in making those. Okay, talking a little bit more about the interaction of X-rays with other things. X-ray energy is lost through interaction. It bumps into things. So an X-ray is shot out of the machine. It's shot towards a person, and it's going to interact with different particles and different atoms in the air, even before it reaches the patient's face, but then it's going to interact with the skin, the muscles, the bone. It's going to interact with things all the way through, and so every time it interacts with another atom, it loses some of its energy. Now, that's a concept I wanted you to understand, but there's two types of ways that happens. The photoelectric effect means that either all or none of the energy was lost. Okay, so think about if you know anything about, or if you're familiar with playing pool, sometimes the cue ball, you'll hit it and it goes down the table and it'll hit another ball. In the photoelectric effect example, the cue ball would hit another ball, the cue ball would stop, and the other ball would start moving. So in that case, the X-ray hit another electron, took its place, and bumped the electron back out. So the X-ray got to be an electron again, sitting in the little shell orbiting the atom, but it kicked out the electron that had been there. Okay? Then that electron is going to go around trying to find another atom to be in. So that's photoelectric effect. Comp and scatter, the X-ray collides with an atom, the electron is bumped out of its orbit, the X-ray lost some of its energy, but didn't take its spot. So again, back to our visual of playing pool. So you hit the cue ball, it hits, let's say you're breaking the original triangle. So you've got all the balls there, the cue ball comes down, it hits, the cue ball keeps going, but the electron, the other ball, is rolling too. So now instead of having one projectile, the X-ray, you have two projectiles. So now you've got the X-ray, which can go to another atom and bump out another electron, and you have the other electron traveling, and it can go do the same thing. So with comp and scatter, you get more damage, because instead of one projectile, now you have two. Well, if those two interact with another atom, and they both cause comp and scatter, which may not happen, one of them may go photoelectric effect, but now you would have four. So you're multiplying how many projectiles you have, and remember, every time this interaction happens, you're causing damage. If it's in the tissue or in the patient's body, that's causing damage. So the more projectiles you have, the worse it is. So comp and scatter causes more damage, but those are the two ways that X-rays interact with different atoms. Specifically, we're more concerned with once they're in the body tissues. And the last slide in this recording is going to be talking about impulses. When we talked earlier about the timer, we didn't get really specific about the timer, but there are 60 impulses per second, and that's how we measure the exposure. It used to be in minutes, and then it was in seconds. Now the exposures are so short that it's fractions of seconds. So you actually would talk about the exposures in how many impulses it was. 8 impulses, 10 impulses. And so you're breaking down even a second. And just fun fact, the reason that it's 60 impulses per second is that is how our electricity in the United States cycles, is 60 cycles per second. And that's why if you go to Europe, you have to have a converter, because their electricity is a little different. But that is the end of part 2.